All right, let's dive right into this explainer. Today, we're going to discover how the seemingly abstract language of mathematical graphs can actually tell a pretty thrilling story, specifically, the story of a skydiver plummeting toward Earth. You know, you might think physics is just a bunch of dry numbers on a page, but as we're going to see, those numbers literally dictate life, death, and everything in between when gravity gets a hold of you. Here's our game plan for today. First, we'll master the hidden language of motion. Then we'll learn how to extract crucial data like acceleration and distance. After that, we'll introduce the physical forces of our atmosphere. And finally, we'll apply these new superpowers to a high-stakes, real-world scenario. So, part 1, the language of motion. To really understand movement, we first need to make sure we're reading the right map. Okay, I need to issue a quick warning right out of the gate here because these two types of graphs look incredibly similar, and it is a classic trap to get them mixed up. Always double-check your y-axis. A distance time graph is tracking your total ground covered over time, but a velocity time graph, which is actually our main focus today, tracks your actual speed or velocity as time ticks by. If you read a velocity graph as if it were a distance graph, you are going to draw completely wrong conclusions about what the object is actually doing. Now, what's really interesting here is how the steepness, or the gradient, of these curves directly translates to acceleration. See, a flat, horizontal line doesn't mean you're sitting perfectly still. It actually means you're cruising at a constant speed with zero acceleration. A straight upward slope, that means you're steadily speeding up, while a downward slope means you're decelerating. And if the line curves, well, your rate of acceleration is actively changing. The shape of the line tells you exactly how the speed is behaving in real time. Moving right along to section 2. Let's see how this builds into actually calculating how fast we're speeding up and how far we've gone. Time to do a little bit of detective work. The crucial takeaway here is that you can calculate your exact acceleration just by finding the gradient of the line on a velocity time graph. You do this by taking your change in velocity and simply dividing it by the change in time. For instance, if your speed goes from 0 to 3 meters per second over the course of 2 seconds, you just divide 3 by 2. Boom, your acceleration is exactly 1.5 meters per second squared. Basically, the steeper that gradient is, the higher the acceleration. But what if we want to know how far we've actually traveled during that time? To find the total distance, you have to look at the area underneath the curve of the graph. If you have a line that slopes up and then flattens out, don't worry, you don't need complex calculus to find the area. The easiest method is just breaking the space down into simple geometric shapes. You carve out a triangle for the sloping acceleration phase and a rectangle for the flat constant velocity phase. You calculate the area of the triangle, so half the base times the height, and add it to the area of the rectangle, which is just base times height. Add them up, and you've got your total distance covered. Now, I want you to just accept this odd little quirk of physics math. Even though we are mathematically calculating an area, which, is normally squared, our final answer for distance is always just in regular meters. You're using an area to find a linear distance, so just remember to leave the squared off your final answer. Of course, lines aren't always perfectly straight. For tricky, curved graphs, here is a super simple hack. Just count the grid squares underneath the curve. You tally up the full squares, creatively piece together the partially filled ones to make whole squares, and then multiply by whatever distance one single square represents. It's that easy. You suddenly have a highly accurate estimate of your total distance traveled. All right, with our mathematical toolkit fully loaded, let's introduce the physical forces that actually pull us back down to Earth. It is time to take these concepts out of the classroom and up into the sky. Take a look at this. This brilliantly illustrates an object in true, pure free fall. Notice the arrow pointing straight down. When an object is dropped from a height, it initially experiences a constant acceleration due entirely to the force of gravity pulling it downward. In this purely hypothetical moment, there is absolutely nothing pushing back against it. If there were no air at all, this would be the only number that mattered. On the surface of the Earth, the acceleration of a free-falling object, before anything else interferes, is a constant 9.8 meters per second squared, meaning every single second you fall, your speed increases by another 9.8 meters per second. But reality check. We don't live in a vacuum. We live in a thick soup of gases called the atmosphere. So as a falling object accelerates downwards, its speed naturally increases. And as it moves faster, it has to physically smash out of the way an increasing amount of air molecules. This whips up more and more air resistance, pushing upward against the falling object. This upward push gradually shrinks the overall downward resultant force. And because the net downward force is getting smaller, the rate of your acceleration begins to decrease. Make no mistake, you're still speeding up, but you are speeding up at a slower and slower rate. Which brings us to our final section, reaching terminal velocity. This atmospheric tug-of-war between the relentless pull of gravity and the growing push of air resistance leads to a pretty thrilling concept. When that upward push of air resistance finally perfectly matches the downward pull of gravity, which is your weight, something amazing happens. The forces completely cancel each other out. The net force becomes exactly zero. And as we learned from our graphs earlier, when there is no net force, there's zero acceleration. The object just stops accelerating entirely and hits what we call terminal velocity. It continues to fall, absolutely, but at a steady, constant, maximum speed. Now, let's tie this whole shebang together. Notice how the physical force arrows directly dictate the dramatic winding shape of the speed-time graph during an actual skydive. This right here is the beautiful translation of invisible physical forces into a very real visual story. Let's break this dive down phase by phase. Phase 1, the jump. The absolute second that skydiver leaps, gravity completely dominates. The skydiver accelerates rapidly, which is shown by that very steep initial curve. But as they fall faster, the upward push of air resistance grows, shrinking the acceleration. The steep line curves and flattens out until the upward drag perfectly matches the downward weight. They've just hit their first terminal velocity, plummeting toward the Earth at a constant, extremely high speed. But obviously you can't land at that speed unless you want to become a pancake, right? So, phase 2. The parachute opens. An enormous canopy suddenly catches the air, creating a massive upward unbalanced force. This causes a sudden, intense deceleration. Notice that dramatic plunge in velocity. The skydiver is definitely still falling, but they are slamming on the brakes hard. And finally, phase 3, the safe descent. As the skydiver slows down due to the parachute, that intense upward air resistance also begins to decrease. Eventually, a new balance is found. The upward drag of the parachute perfectly matches the downward pull of gravity once again. The forces are balanced, the deceleration stops, and the graph flatlines one last time. This is a brand new, completely different terminal velocity. It's a much slower, constant speed, one that allows for a perfectly safe, gentle landing on the ground. And the graph simply stops when velocity drops to zero at impact. So we've seen how the atmosphere acts as this giant, life-saving cushion, turning what would be a lethal acceleration into a survivable terminal velocity. I want to leave you with a final thought to chew on. If friction with the air is ultimately what balances the forces and saves a skydiver's life, how terrifying would this velocity time graph look for someone falling on a planet with gravity, but with absolutely no atmosphere? Without that air resistance to flatten the curve, what on earth would happen to that line? Keep exploring, keep questioning, and we'll see you in the next explainer.